Hello again, Woken Way, 1.3c. We're going over increasing and decreasing intervals, absolute, relative, maximum, minimums, even, odd, and neither functions all in one lesson. Well, actually, the first two things here we're going to breeze right on through because we should have explored this in class, but just in case you weren't here, we are going to take a look at this. So the first thing that I asked you to do, or that you were asked to do, was to take a look at these two graphs and look at this over here, which talks about where the graph is increasing and decreasing, and then make some connections. So you can see this says the graph is increasing from negative infinity to negative 6, and then from 2 to 6, and you're like, looking at this graph, what I wanted you to pick up was negative infinity to negative 6, and then from 2 to 6. So if I read this graph from left to right, those are the intervals on which the graph is going up the hill. And then I also am going to look here, which is this next part, from negative 6 to 2, and from 6 to infinity, it's going down a hill. So those are the intervals on which the graph is decreasing. So you do the same thing for graph 2, you go on through example 1, and hopefully you pick these up. I'm going to put them all up here so that you can get them. If you didn't get a chance to do this in class, then you really need to pause the video and make sure that you get what increasing and decreasing is. So the way that increasing works is we always read our graphs from left to right. And if you're reading it from left to right, you should, if you're going up a hill, it's increasing. And you report the x values. So think about this. If you were to report the y values, that would be redundant because you already know you're increasing. You already know you're going from low to high. So we're more interested in the width of that low to high, or the x's. So how long am I increasing for? From what x value to what x value? So one other thing that I want to point out is there are no brackets. Because increasing, if you say something is increasing, it's a comparative word, meaning that you would need us to have more than one location. If you go to an endpoint and I just say, oh, that x value is negative 7, is it increasing or decreasing? At negative 7, that question doesn't make sense. If I say from negative 7 to negative 8, is it increasing or decreasing? That question makes sense. But at one instantaneous location, that doesn't make sense, which is why whenever we're doing increasing or decreasing, we never have brackets. Kind of like whenever we talk about negative infinity, infinity, but for two different reasons, okay? So again, increasing and decreasing are comparative words. So moving on to decreasing from left to right, you would be going down the hill, okay? So there are definitely points in a graph where you start to switch and go down a hill. This is called a turning point. We'll get into that. But I'm just going down the hill here. So I already know I'm decreasing. How long am I decreasing for? And from a graph, the way that we can read that is from an x value of 3 to an x value of 9, you're decreasing. So that's where that comes from. So keep that in mind. So that was increasing and decreasing. You're given the technical definitions up here of increasing and decreasing. And then there's also one called constant. That's just where you're going flat. We might have some graphs like that, but I think you guys can pick that up. The next thing that was expected of you guys in class was to figure out your own definition for relative max and relative min. So we gave you some examples of those and I've highlighted them. So this is considered a relative max. It has a value of 7 or a height of 7 when x equals negative 6. And then this also happens when x is positive 6. And then we have a relative min of negative 4 when x equals 2. So those are relative mins. Notice that there are 2 points down here that look like minimums, like the lowest point on the graph, but they're not labeled as relative minimums. So that's because they're absolute minimums, which we'll get into in a second. But let's start here with relative minimums. Make sure you have all these down. So you can see there's a relative minimum. It was kind of hard to pinpoint exactly where it's at, but it's right where this is going concave up and then it's turning and going concave down. So just be careful with those right there. So again, it's the turning points. If it's, let's give those definitions in our words actually. So if it is a turning point, if it's a peak of a hill, then it's going to be a relative max. And if it's the base of the valley, then it's going to be a relative minimum. And you report the y value when x equals something. So it's a two-parter, but you don't write the point. That's just not the way they do it. So again, context, I guess, is how it's going to help you. But we just are always going to write it like this, so you shouldn't need much more than that. And then again, they're not the endpoints because they're relative max and they're over an open interval. So in math, when we talk about open interval, if I'm just kind of going to look relatively to my whole graph, I just kind of zoom in there, that would be a relative max. But when I look at something like this, because it has endpoints, that would be a closed interval. But whenever you're doing relative, it's assumed that you're over an open interval. So you're kind of relatively speaking, zooming in on a part of your graph. So that was the relatives. This group work 3 is actually the absolute max and absolute mins. And so I do have highlighted on this graph that there is a relative max there and a relative min there because those are turning points. That's the peak of the hill. That's the base of the valley. But when you look over here at absolute max, those aren't on there. That's because absolute max and absolute mins are absolute, meaning they are absolutely the highest point on the graph and absolutely the highest points or the lowest points on the graph. So you have to keep that in mind. It doesn't matter if they're a turning point. Look at that. Look at graph number 6. Those are turning points down here. They are still absolutes. They're more specifically absolutes than they are relatives, I guess. But if you put both of those or one and not the other, I would have to give it to you because they meet the qualifications for both definitions. Because if you look at this as from left to right, that is a closed interval, which is part of the definition. If you look over in the top right, you can't see it, but you can see it on your paper. It needs to be a closed interval. But again, that relatively speaking, I can relatively look at that piece of my graph and call it a relative too. But without a doubt, if it's the lowest point or the highest point, then it's an absolute, okay? So then in this example right here, you tried that on your own. So you had to figure out your absolute max. So your absolute max actually happens to be a relative max as well, but your absolute min, which is this point down here, does not happen to be. It's solely an absolute max. There's no turning point, so it's not a relative. So let's take a look at the layman's terms of those definitions. First of all, an absolute max is the highest overall y value, and endpoints are okay on that one, and you do y value when x equals blank. The absolute minimum is the lowest overall y value, and the endpoints are okay again, and it's a y value when x equals blank. Okay, so again, relatives are turning points and absolutes can be turning points, but more specifically, it's your highest overall y value or your lowest overall y value. Okay? Now, that brings us to the only part of the lesson that we didn't get to in class, which was even and odd functions. And we do a lot of even and odd in this class and in calculus as well. So make sure you memorize how to test if something is even or odd. So our first definition is an even function. And what this is saying is when you plug in a negative x value, you get the same thing as if you plugged in a positive x value. Whoa, what? Yes, you plug in a negative x value and you get the same thing as when you plug in a positive y value. So you would have these coordinates. So those even graphs have symmetry about the y-axis because you have your negative x with the same height as your positive y and your positive x with the same height as your positive y. These don't obviously always have to be positive. These could both be negative, but they're the same value. What about odd functions? This says the function f is an odd function if when you plug in negative x, you get the opposite, that's what a negative sign means in math, of what you would get if you plugged in positive x. So what that means in terms of coordinates is if you plugged in negative x, you would get the opposite. So this is what it means, negative x, negative y. So if you plugged in x, you would get y. If you plugged in negative x, you would get the opposite of what you got there. Super interesting. Okay, great, good to know. How do we know whether or not an equation by looking at it is even or odd? Now back in Algebra 2, you may have just looked at the highest power of x, which is not exactly the right way to go about that, but you again are progressing in your math education, so it worked for what you were doing in that class. It won't work for what you're doing in this class. So based upon this definition, it looks like we need to plug in negative x. And if we plug in negative x and the function stays the same, like here, then it's an even function. And if we plug in negative x and every term changes signs, then it's an odd function. If we get a mixture of both, it's neither even nor odd, and we can't use that conclusion. We can't use even and odd properties to help us with whatever we might need help with. So here's what we're going to do. We're going to plug in negative x and simplify. Make sure you put in parentheses around that negative x. Remember, disciplining yourself to work things properly is huge. So that would be negative x cubed times 2 would be negative 2. And then this is going to be negative x to the 5th, but I have a negative 6, so it's going to look like that. Then what I'm going to do is I'm going to take this answer, compare it to my original, and see what happens. So 2x cubed, change signs, and negative 6x to the 5th, change signs. Because both terms change signs, this is an odd function. Okay? Let's do the same thing over here. Let's plug in negative x. Oh no, there's the square root. It's okay. Just follow what you are told. Follow the math. It tells you right here in all this definition stuff. So that gives me x squared times 1 minus, and negative x squared squared is x squared. So if I take this and I compare it to that right there, everything stayed the same. So this is an even function. And then let's try this one. Now, in order to try this one, you first need to multiply this out. So no puppies will die. So we will FOIL that or multiply that out properly. So here is the one I'm going to compare it to. So I'm going to put it in standard form. That way I can really see if each term, standard form would be terms, changes sign or not. So let's plug in negative x squared plus 4 times negative x plus 5. And that gives me x squared minus 4x plus 5. Now, some of you are able to mentally do this, but remember, you're disciplining yourself to defend your answer mathematically. So I know you can say, is the function even, odd, or neither, and you can do the mental math for it, but defend your answer by showing the math. Okay, so x squared stayed the same. These change signs. Once one stays the same and the other changes signs, it's neither even nor odd. And real quick, just because I have a little bit of time here, I want to show you what these graphs look like, just so that we can see. So I'm going to go up here. You don't know how to type these in yet. That'll be the next lesson, but I want to show you anyways what I mean by symmetry with respect to the origin. So here is that first graph in A. It looks like that. So do you guys see right here? These points right here would have the coordinates like negative x, positive y. And if it's odd, you should be able to flip those and get the exact same coordinates. So you should be able to do the opposite. So you should be able to do positive x, negative y. So that is an odd function. And when we did the inverse function, not the inverse function, when we did the even odd test by plugging in negative x, we got that. Let's take a look at that one. I have no idea what that even looks like. That's so interesting to me. We'll soon find out. So there I am, typing that into my calculadora, and then I hit graph. Whoa, you can't even see it. Let's zoom in. Oh, so cool. Still symmetry. There is symmetry with respect to the y-axis on that one. Do you see that? Here is like a point right here, and this has a positive x and a positive y, and right up here we said it should have the opposite but the same y. So opposite x's, same y's, and it does. So cool. Okay, let us do the other one too. Hold on, my calculator's thinking. So I'm going to do that last one down there, which says x plus 2 squared plus 1. And we're going to take a look at this parabola. Do you guys see there's no symmetry? So if I pick a point on this parabola like this right here, let's say that's the point. I know it's not, but let's say, you know what, actually it is. Negative 2, 1. This is the point negative 2, 1. If it's symmetric with respect to the y-axis, meaning it's even, then I should see the point 2, 1 right here. So I change the x but keep the y, and that point should be on the graph too, and it's not. And if it's even, I take that and I switch both x and y. So negative 2, 1 would be 2, negative 1, so it should be somewhere over here, and that point is also not on the graph, so it's neither even nor odd. So let's just revisit this one more time on here. We can do that with this graph right here. So we have negative 3x squared plus 2, and you guys can see I've written some little tips for you. If it's even, you can think, yes, y-axis, even, same, meaning it has symmetry with respect to the y-axis if it's an even graph, and if it's even, all your terms will stay the same. So if I were to graph this right here, this graph is x squared, it's going to be stretched by 3, then I got to reflect it and move it up 2. So what this graph ends up looking like, there's that stretch by 3, is this. Do you guys see that symmetry, first of all, with respect to the y-axis? And then I also want to take a look at this point right here, which is 1, negative 1. And then remember, the symmetry thing that we talked about before with coordinates is the y-coordinate will stay the same if it's even, and the x one will change signs. And look, that's exactly what happened right there. Okay, so if xy is on the graph, negative xy is on the graph. Alrighty, moving on up. Negative x cubed. So this graph actually looks like this. We know this already because we can graph x cubed and then we just need to reflect it. But this has the point. Let's do this point. This is the point 1, negative 1. Remember, if it's odd, odd is opposite. You change both. So negative 1, 1, that's on the graph. So, oh, I get it. Oh, if it's odd, it has symmetry with respect to the origin, meaning it's reflecting in both x and y. It means you're going diagonal. And if it's odd, all your terms will be opposite. Not just some of them, not just part of them, all of them. And that is it for today's lesson.